Record on. Okay, it's 10:05. I think that's enough time. So welcome to the first Gemmini tutorial that we've ever hosted here at IISWC. So since this is the first one, if you guys have any suggestions or advice afterwards, we'd love to hear them. You guys are always welcome to email us with suggestions. My name is Hassan Genç. I will be presenting. Dima and Simon are also in this meeting. If you guys have any technical issues, you can message them and they'll try to help you solve them. Yeah, so before we begin, we'd like to acknowledge our funding. We're partially funded. Oh, sorry, one other thing before I start. I know people are in like crazy time zones right now. So, you might be in your pajamas or anything, but if you are able to, and you can open your video camera, I'd really appreciate it. It would make me feel less awkward. And this is meant to be an interactive activity. So, feel free to interrupt at any time. I won't get mad. Ask any questions you want as we're going along. The more, audience participation we get, the better I'll personally feel. Okay. So before we begin, I'd like to acknowledge our generous patrons, the US government. We're partially funded through the DARPA RTML program, but of course, legally speaking, none of our views or conclusions necessarily represent the opinions of the US government. Okay, so we have 4 sessions planned with a quick preliminary setup as well. We are going to talk about Gemmini's motivation, why we built the system in the first place, and the hardware architectural template. Then we're going to go more in depth into the programming model of Gemmini and how you can make your own changes to Gemmini programs. Then we're going to talk a bit about how you might do performance profiling on Gemmini to try to find bottlenecks or causes of slowdowns on DNN workloads. And finally, we'll have some quick parting thoughts with a conclusion and future work or what we're working on right now to expand Gemmini. As part of this tutorial, we've created lots of new scripts to make it easier for people to run everything. So even if you're familiar with Gemmini, some of these scripts might be new to you. Okay, so everybody should have gotten an email from Dima explaining how to log into their AWS instance. If you didn't register for this tutorial, then you wouldn't have gotten an email. So in that case, please contact Dima and Simon as quickly as possible. We have some spare AWS instances, so we could get you guys set up on those. This should also be in the email that you got, how to log into Docker. We're going to do everything through Docker. And a quick warm-up script. This may or may not be necessary, but it might make some of your for the future commands run a little bit faster. And all of the instructions in this document, in this tutorial, you can find on this URL over here, tiny URL IISWC tutorial instructions. Simon has also posted the full URL in the chat. So if you fall behind at any time, you can catch up from there. And also, if you think I'm going too fast through any of these commands, just let me know and I'll slow down. Okay, so the first of our 4 sessions. What was the motivation for building Gemmini and what did we eventually end up building to try to address that motivation? Yeah, why did we build Gemmini? So it won't come as a surprise to any of you to hear that DNNs are becoming very popular and people are trying to get them running on everything from the actual physical cloud in the sky to cars on the street to phones in your pocket. Unfortunately, these DNNs have very high computational requirements, which means that DNN accelerators have to be designed to actually run these workloads in an efficient manner. So these DNN accelerators are also being put into everything from small edge devices to power-hungry cars to huge cloud warehouses. However, designing new hardware accelerators is obviously a very difficult, expensive, and time-consuming task. But every new physical environment will impose its own resource constraints, which means that many different types of accelerators are needed for different environments, and edge products are constantly being churned out by industry. And that means that accelerator generators are also exploding in popularity. These generators allow architects to change a few parameters or maybe a few lines of a DSLR configuration file and develop a new accelerator for a new environment at little extra cost. Existing generators each push forward the state of the art in different and important ways, but they don't give architects all the tools they need to evaluate the impact of the full system and full stack on performance, and the ability to see how different components of the system and software stack may interact with the accelerator itself. Now, when we discuss the full system, what do we mean exactly and why is it important? Well, the system, as we use the term, encompasses everything from the SoC all the way up to the operating system running on the SoC. The actual physical SoC can greatly reduce the maximum performance of the accelerator if its resources have not been well distributed among competing components. If we zoom in past the SoC itself into the memory hierarchy, not just of the accelerator's private scratchpad, but also of other CPUs and shared outer caches, they can all impact overall performance, either in subtle ways, such as through cache coherence policies, or much more directly through miss rates and miss or hit latencies. The virtual address translation system, which includes the TLBs and page table walkers, also impacts performance due to the possibility of page faults and TLB misses. Then at a higher level, there are the host CPUs themselves, which can actually have significant impact on total performance if there are any kernels in your DNN that cannot be efficiently offloaded to the accelerator, which is more likely to happen in the field of machine learning, where new, unusual, and unexpected algorithms are often developed for new networks. And finally, there is the operating system itself, running on the host CPU and supporting the DNN workloads that must be accelerated. So the operating system affects both the correctness and the performance of the DNN accelerator because it forces architects to reckon with new kinds of memory protection, as well as with interrupts, context switches, or other unexpected events that may harm total throughput if they have not been accounted for. We personally experienced lots of very annoying bugs when we moved off of the bare metal environments to a Linux system, just due to these unpredictable context switches. Above the system, we have a full programming and software stack that DNN accelerators must be able to interact with while preserving performance and energy efficiency. Some DNN accelerator generators allow users to program their accelerators using only high-level APIs, such as TensorFlow or Onyx, which define the structure of the neural network, but do not necessarily define how it is to be offloaded. Others will allow programmers to call functions at a lower level, which offloads particular kernels, making them easier to integrate into new applications, but a bit harder for programmers to program. And finally, some accelerator generators allow users full control, full control over the hardware's configuration and its low-level ISA, which allows dedicated developers to extract the maximum performance necessary, but which also greatly increases the developer's cognitive burden. I see there are some comments. Okay, they're not related to me. Yeah, if you have questions, just say them out loud because I will not see them in the comments. Okay, so where does Gemmini sit upon this system and software stack? Well, unlike prior accelerator generators, Gemmini allows users to evaluate this full space as well as to tune the hardware accelerator itself. Prior accelerator generators cover only a subset of the space because they're usually trying to advance the state of the art in one particular corner of the space, but Gemmini covers a superset of what they cover in order to provide architects with a comprehensive platform for their own design space exploration. Gemmini's hardware template is relatively flexible, but it always follows the pattern shown here in these diagrams. So we will zoom into different parts. At the heart of the accelerator is a spatial array, which is meant to perform dot products and is meant to perform the most computationally heavy parts of DNN workloads. It can be parameterized to support different data flows like output stationary, wait stationary, or to support both of them so that programmers can choose between them at runtime. It can support different dimensions and different levels of pipelining. The spatial array is composed, excuse me, of a two-tier hierarchy with combinational tiles, each of which is composed of many smaller PEs. And each PE performs basically a multiply accumulate operation with either the wait stationary or output stationary data flow. Now, by just choosing the size of these tiles and the dimensions of these tiles, you can go from something that's fully pipelined, like a strict systolic array, which is maybe similar to the original TPU, to something rather where each tile is performing a larger dot product or vector operation, so that you instead end up with a system with parallel vector engines, maybe more like NVDLA. Right. So surrounding the spatial array, we have a lot of non-gem function. Well, maybe not a lot, but we have non-gem functionality for transposers, different types of data transformations, reshaping, matrix scalar multiply units, activation functions like ReLU and ReLU6, and other miscellaneous operations like max pooling. And if you think you don't need any of these, the architect is free to optimize these out at elaboration time. The spatial array and the peripheral circuitry gets data from the local scratchpad and feeds results either back into that scratchpad or into a wider bit width accumulator, which can be used to accumulate partial sums. Architects can decide what the capacity of this local memory is, just how heavily banked it is, whether it's single or dual ported. They can perform these kinds of trade-offs through Gemmini's configuration options. And this local scratchpad memory reads data from and writes results back to the shared memory, the shared cache hierarchy, which is shared not just with the accelerator, but also with the CPU and with any other components or accelerators on the chip. So the capacity banking strategy, size of the ways and all the typical cache parameters can be controlled here. You can also control the depth of this hierarchy. For example, you can add L3s, and you can even play around with different options for the DRAM controller. Yeah, then there is a host CPU, which is adjacent to the accelerator itself. The host CPU basically feeds results, feeds commands and instructions into the accelerator. And then it reads the results that are written back out into the shared main memory system. The host CPU can be configured to be in order, out of order. You can change the ROB capacity, the L1 capacity, the branch predictor, lots of different options. Then there is the virtual address translation system. This is used so that programmers don't have to manually translate addresses when feeding them into the accelerator. Gemmini has a local TLB, and it shares a page table walker with the host CPU, through which it can get virtual addresses. And you can change the TLB hierarchy. For example, you can add an L2 TLB so that you have a multi-level TLB system. You can flatten that hierarchy, you can change the capacity, et cetera, et cetera. Oh, oops, we already talked about this. Oh, sorry, I'm pressing the buttons in the wrong order. Give me a moment. Okay, so Gemmini gets instructions from the host CPU. Those instructions are fed into Gemmini's local controller, and it uses a reservation station to basically resolve dependencies and maintain program order. you can tune the size of this reservation station as well. You can have full entries. You can try to save space with partial entries that only support load and store commands. We also have a branch where we have experimented with out of order support for this reservation station. That will be merged in soon, but it's not ready right now. Then we have loop unrollers within Gemmini. Programmers can write their own loops using instructions that have been fed in from the CPU. But there are some loop patterns which appear very often. And for those, we have FSMs which can accelerate those loops by unrolling them in hardware and dynamically scheduling the operations to get good overlap, maybe better than a static schedule can. These can be parameterized as well. You can have either just inference loops just for inference kernels or for both training and inference kernels. Yeah.
Can I ask a question? So why do we need a reservation station, and why do we need like, we need like this reservation station for reordering the instructions, right? But let's say in a DNN execution, most of the scheduling can be identified at static time in the compiler. So doing it on the hardware, won't it result in more latency or like performance impact rather than doing it on the compiler?
So when we initially created Gemmini, actually we didn't have a reservation station. The programmer was responsible for ordering all commands and expressing the dependencies between them.
I see.
To be honest, it was just very difficult to program that. This allowed us to get much faster, to iterate much faster on our software library. Beyond that practical reason, most of Gemmini's ISA commands are very low granularity, like about the size of the spatial array itself. So for those, it's a little bit harder to actually, predict the exact latency of when a small submatrix will be fed into the reservation station. So we've experimented with some linear algebra workloads that we're not talking about over here, where we find that this being able to do things out of order can actually help performance for some types of workloads where latency is harder to predict and is much more critical. Yeah.
Thank you.
Yeah, no problem. But yeah, this was just our decision. If you have a really good compiler, you should be able to predict to a good confidence. And maybe we can add that as another option in the future. Basically bring back that feature that we tore out a long time ago to statically schedule these. Okay, any other questions or? Okay. Then zooming out past Accelerator, we have the full SoC. You can have as many Gemminis as you want on an SoC, on a chip. You can have, as many host CPUs as you want that are each using their own Gemmini. These all communicate through a shared memory system and a shared cache hierarchy. Okay, so somebody asked privately, is the reservation station for out of order purpose? Yeah, yes. By default, it has, I guess you could say limited out of order capability, in that it reorders instructions across different execution pipelines, but not within the same execution pipeline. But we have a branch where we've also experimented with allowing reorders within the same execution pipeline, and that should be merged in. Yeah, and okay, let's keep going then to our first interactive activity. We will try.
Sorry, I have a quick question. So it looks like, I think in your documentation, you say you have this decoupled access architecture. You have a 3 queues. Yeah. So I was wondering, who is responsible for the synchronization? Is it the compiler?
No, so it's this reservation station, basically.
Oh, I see.
So
And how, yeah, can you elaborate that a little bit how that works? Yeah. So this is hardware, right?
Yeah, yeah.
Mm.
It's not that different from any reservation station you'd have in a CPU. We actually have an undergrad now who's working on different optimizations for it to reduce its area. But maybe then it'll be a little bit more innovative. But right now it's fairly typical. So, you know, there's store instructions, load instructions, execute instructions. Right now, by default, it will assume that all the instructions within the same execution pipeline are going to operate in order. So it doesn't need to do complicated reordering between them. But it checks for, you know, read after write and write after read dependencies between different execution pipelines. And it won't issue instruction. So every instruction coming in from the CPU goes into this reservation station, and they won't be issued out until all of the dependencies are resolved.
Okay, I see.
Yeah.
Good. Thank you.
Yeah, no problem. And yeah, like I said, initially it was the compiler's responsibility, but that was in the very early days when, you know, we were the compilers, basically.
I see.
So yeah, so if people want to add that back in as a feature, we can certainly do that.
So so yeah, because like I read this decoupled access architecture original paper, then it's like the definition of decoupled access here and the original decoupled access architectures seems, I think, a little bit different, right? I think here you have this reservation station, which seems basically like traditional, like reordering buffer, like registers, like you are managing it here. And the original decoupled access architectures, I think they have the compiler basically takes care of the synchronization.
Yeah, I guess that's a good point. Yeah, it's been a few years since I read it. Initially, you know, it was designed by the programmer. That's when we gave it this name. I guess later on we changed it, but maybe we didn't reassess whether that name works. Yeah, that's a good point. We can be more careful with the definitions, maybe.
Right.
Yeah.
Yep. Thank you.
No problem.
I have a quick question as well. So, I'm wondering, how does multitasking or like threading is managed in the Gemmini?
Right now, it isn't really. You know, you can have different cores, of course, and each one can be using its own accelerator to do a different task. But right now, we don't have good support for you know, two different cores sharing the same accelerator. We would need to. Yeah, part of the problem is the scratch pad and the accumulator can be pretty large. So, you know, I guess we need to make difficult design decisions. You know, should that all be spilled out if one of them tries to use too much memory? Yeah, that would be those would be interesting trade-offs.
Okay, yeah. So right now, if say a thread is using the Gemmini core and something else wants to use it, so does it just evict everything and then?
So right now in the default designs, there's just one. Each CPU has its own, so we can't access the other one. But if we were to configure it differently, so that they could each access the same one, they would basically have access to each other's like memories, basically, like local scratch pad memories. Yeah. We don't have protection for that right now. There was a class project a few years ago that somebody worked on for one of our classes, where he added very basic like memory protection, but it wasn't very sophisticated, you know. So it would just basically zero out data if somebody else tried to access it, which isn't ideal.
Okay. Yeah.
Yeah.
Thanks.
Yeah. No problem. Somebody asked the performance. Wait, sorry, I think there are a few questions. Does it support multitasks? I think we just answered that. How can OS manage between different threads? I guess we also answered that. Each one has its own accelerator. And right now, they're not sharing between accelerators, at least not protecting local memory between them. The performance in the Gemini DAC paper, was that compiled with the loop ISA? Yes, but we have made more optimizations to the loop, this loop unroller since that DAC paper. So in our presentation for DAC, we're actually going to update the results of it. There are specific types of shapes where the trade-offs are a little bit different in how you want to schedule them on the loops. So we basically added support for like a greater diversity of like tensor maybe shapes and trade-offs. So the performance is a little bit better than that, but it was using these loops. Yeah, so I guess that's maybe a philosophical discussion on, is it better to statically schedule or dynamically schedule? But yeah, and you don't have to use this loop unroller, to be absolutely clear. You don't. It's only like a performance optimization. Functionally, it doesn't add anything. You can run the same commands without it. Okay, those are great questions. Thank you. Does anybody have any other questions? Okay, let's go to the first activity, where we will basically use new scripts that we created for this tutorial. And so this was a good exercise. It forced us to make ourselves more user-friendly. And we will use them to basically play around with Gemini's configuration and maybe build like different simulators for RTL. First, just try to run this command, set up paths within the Gemini directory. This basically just sets up some symlinks so that you can access the different configuration files. Let me zoom in a lot. And give me a second. Yeah, so just scripts, set up paths. And now if you look inside configs, you should see several different configuration files. Okay. Afterwards, we can see the Gemini configurations. So first, let's open up the default configs in Gemini default configs.scala. So that's configs, Gemini default configs. I think this is what our, if I recall correctly, was what our reported performance numbers were for in our papers. You have a lot of different data configuration options here. You can change the data types that it's operating on. You can change the data type of the partial sum accumulations. You can also change the width of the operations coming out of the spatial array itself. For example, if you know that you have a 16 by 16 systolic array and you're getting 8-bit inputs, the largest possible output would be 20 bits. But it maybe if you're just using FP, just 32-bit values, you don't want to expand it anymore. You can change the size of the spatial array, the level of pipelining within it. This is that two-tiered hierarchy we mentioned previously. You can change the data flow. You can make it either support both data flows, and the programmer can decide between them at runtime, or you can do the OS or WS data flows, wait stationary, output stationary. You can change the capacity and banking strategy of the scratchpad and the local memory. There's some Boolean options. Do you want to support training convolutions in the loop unroller? Do you want to support max pooling? Do you want to support activation functions? If you just want like a raw math mode accelerator, that was like those features probably wouldn't be necessary, so you can leave them out. The size of the reservation station, the size of the different load, store, and execute instruction queues. You can play around with the DMA, just how much in-flight instructions can it have at once. The TLB size. These operations look kind of complicated. You can basically decide exactly what the matrix scalar multiplications, how they're defined. For example, maybe instead of like a straight multiplication, you would rather want just a bit shift or something like that. But the only reason this looks complicated is because we're using floating point values and multiplying them by integer values in our default example, and Chisel doesn't have very good support for floating point operations. If they were both signed integers, it would just be like a one-line thing like that. Okay. Just more major scalar operations. You can change how many counters Gemmini has. You can change how many scratchpad and you can basically change, these are miscellaneous options. If you're just doing a weight stationary data flow, you might not actually want to write results into the scratchpad ever. You might always just be writing them into the accumulator to accumulate partial sums. So you can decide just what the connections are between local memory and the spatial arrays and functional units. Then we can open up the custom configs. So I'll leave this here. Yeah, let me know if I'm going too fast or anything. And we have different custom configs here. We basically just copy the default config, and we can just change different parameters within it. For example, we've made a baseline inference config for this tutorial where it's just a default config, but it doesn't have support for training convolutions. We could make a larger one with a bigger scratchpad, maybe for better performance. We could make a training config where we're actually using floating point values this time. You can decide exactly what exponent and significant width you want. So Gemmini's max pools right now don't actually preserve the information of which indices were pooled. So it's not actually useful for training right now, unfortunately. So you can leave that feature out if you know you're not going to use it. We have a demo config here for complex numbers. We will talk about that soon further on this tutorial. Right now, you can ignore it. And once you've created a configuration above, you can just change this line. Right now, it's saying I want to build a baseline inference config. You can instead make it build, I don't know, the high performance config, or the training config, etc. Okay, everybody following along so far? Okay. You can then see different configuration options for the CPU. For example, let's try opening up CPU configs. CPU configs. So this is basically a convenience collection of CPUs that we created for this tutorial, but we'll hold on to it because it might be useful. Where are the chipyard, which is the framework that we're relying on, comes with lots of different CPUs, and those can be configured individually as well. If you don't want to go through if you don't want to go to the options for those CPUs themselves, you can just pick between the ones that already exist over here. For example, Rocket cores are in order, relatively cheap, maybe not the highest performance. You can make them big or small. Smaller ones are missing like floating point multipliers and different features like that. You can have boom cores, boom being the Berkeley out of order machine. So those are much more expensive, but also much higher performance because they can run operations out of order. And then you just decide which of these you want your custom CPU to be, right? Like if I want to make the boom large cores, I can build those, etc., etc. And each one of these has different trade-offs. For example, the in-order small cores actually don't have good Linux support because apparently parts of the RISC-V Linux kernel expect floating point support, etc. You can decide exactly what type of environment you're running on and what support you want. Okay, is everybody keeping up? Okay, let me know if I need to slow down. We can also see SOC configs, where we put these different components together, basically. Yeah, so you can control which CPU you want, and also which cache, which L2 cache you want to use. You can change its banks, the number of ways, the capacity, what the expected latency of DRAM accesses will be, so that it can tune its performance a little bit. And it basically puts together your Gemmini config, the inclusive cache, and the CPUs. Okay, so once you've chosen your configs, what exactly will get built? Well, first of all, you'll get Verilog. Chisel is written, Gemmini is written in an RTL language called Chisel, which is nice, but unfortunately, there's no tool which can actually ingest Chisel directly, so it'll generate Verilog for you. Afterwards, you can use the RTL to build either a functional simulator, which it won't give you any accurate performance numbers, but it will tell you if your programs are functionally correct. It's fast to run, fast to build, but it's basically just an ISA simulator running on your CPU. So you can't get any waveforms out of it. You can build a cycle accurate simulator, either using Verilator or VCS. In this tutorial, we use Verilator because we can't buy licenses for all of you guys. It's much slower to run, much slower to build, but you get waveforms out of it, so more useful. One downside with the default Verilator and VCS builds is that the DRAM models kind of suck. They are not realistic. They're kind of assuming that any access will take just like one cycle, if I remember correctly, or a fixed small number at least. So there's a wrapper around it called Midas, which basically wraps this Verilator simulation in with a more realistic DRAM model. So this is slower to build, maybe a little bit slower to run, but you get a more realistic DRAM model out of it. And finally, there is something called FireSim, which is basically a tool that was also developed here at this lab to let you run programs generated by Chisel on FPGA accelerated simulations. We won't really go into much FireSim details here because FireSim is probably one of the best documented Berkeley projects, and it's also kind of too large to cover in this one tutorial. But acceleration simulations you produce through it are also cycle accurate, fast to run, but very slow to build, and you have limited waveform support. But the one other advantage is you can run Linux on them because they run fast enough to do so. Okay, so let's try building a functional simulator now. So it's very simple. Let's say you've chosen your configuration option in those SSC configs and stuff. So just run the script. Scripts build spike. This should take maybe 2 minutes. Yeah, and if anybody has any questions while that's running, they can let me know. You can wait 1 or 2 minutes. If it takes longer, the warm-up script actually should have already built this. So in that case, we can just exit out of this and run that. We can give it a minute. Unfortunately, we had a higher attendance than expected, so we had to give everybody cheaper instances than we were originally planning to. But should be fine.
In the meantime, I have a question.
Yes.
How close is the generated simulator using Verilator close to like a RTL implementation? Like, let's say, I'm not very aware about Chisel and like different languages which convert like high-level languages to Verilog, I guess. So just if you could give some insights.
Yeah. So we go up for a second, like this, so this is the real Verilog that will go like in your design, right? This.
Yes, like a hand implemented Verilog.
Yeah, except it's much harder to read than
Yes.
handwritten Verilog. So what's running on Verilator is exactly the right RTL that you will be running. The only difference is when it goes off, like the SOC basically, when it reads outside of the cache hierarchy and needs to access DRAM. That's the only part where it's not realistic. So that's where Midas comes in, which builds on top of this, and Firestone builds on top of Midas actually to accelerate these simulations.
How do they access the memory DRAM? Like, is it like a standardized interface, like some AXI or?
Oh, that's a good question. I am not sure actually. I think it's AXI because when I look through the Verilog source code, I see a lot of lines mentioning AXI, but I have not looked too much into that myself, to be honest.
I see.
Okay, so maybe taking a little bit longer than expected, at least in our test runs earlier. Oh, okay, there we go. So if you guys all start at the same time as me, it should be about to finish. And then we can just reuse that generated simulator for the other things. Okay, so now you have a functional simulator, and we call it Spike. I'm not sure why it's called Spike. Okay, so then you can build a cycle accurate simulator, the Verilator one with the unrealistic DRAM model. So again, once you've chosen your SOC config, you just run this build Verilator script. If you have VCS, you can run build VCS instead. And if you want to build one which can generate waveforms, you can add this debug option to the script, when you call the script. I would actually not recommend running this right now. It will take way too long, especially because Verilator can sometimes be kind of slow to compile. Instead, we have like pre-downloaded these in what we call checkpoints, just for this tutorial. And you can just run checkpoint build Verilator, and it will copy it all over. Let's do that real quick. Yeah, so that basically just copied over some precompiled binaries. But when you want to build your own, just run this script, and it will look in those SOC configs that we mentioned earlier. Okay, you have Midas as well, which has a few more options. So if you run the build Midas script with the help option, you'll see what those options are. You right now you just have 3 different options for your DRAM controllers. You have first come first serve, you have first ready first come first serve, and you have first ready first come first serve with a 4 megabyte L3 basically. And you can decide which one of these you want to build. Again, don't actually build it. You will not finish in time. Just run this checkpoint we made, build Midas. And in fact, once again, the warm-up should have already done that. So if you ran the warm-up, you shouldn't even need to run this. Yeah, that'll just copy things over. Give this a minute too. Okay, I'm just going to Control C out of it for now. If you ran the warm-up, it should already be there. So you shouldn't need to run it again. But in general, you run that build Midas script to build the simulations, the Midas simulations. Okay. The last thing you need to build are the actual software binaries that we run on these accelerators, right? So these are just RISC-V programs that you're going to compile that are going to run on these simulators that we mentioned. So I'll leave this up for a minute before running it myself. You want to go to a directory called software Gemmini rock tests. This is where our software tests exist. Then you can open up this file called template.c. Let's do that right now, just to get a basic insight into what these tests actually are. Open up bare metal template.c. This is basically a template for the tests that other tests are supposed to be similar to, and it's pretty commented. It's basically just initializing some matrices in main memory, moving them into the scratchpad, multiplying them inside the scratchpad, moving the result back out into main memory, fencing till the operations will return, and then checking whether or not they're equal. And if they are equal, it tells you, congratulations. Otherwise, it gets mad at you and tells you that they're different. Okay, so to run these, there's a script called build.sh, which should compile them all for you. Yeah, so just give that a minute too. So the ones which take the longest to build here are hand implemented DNN models. And those just basically take a while to build because the weights are so large. And the compiler, I think, it takes a while to read all of those weights in. Yeah, let's just give this a minute. And this script can also take in certain types of make arguments, like -j1. These are actually all the make arguments because it really just pipes these command line arguments down to the inner make call. Okay, let's give it another minute for it to finish. Otherwise, I will just Control-C because we don't actually need all of these to be done. There we go. They've all been compiled, and you can see the code that was compiled in the build directory. Let's do build ***, and you can see all of them. Here's the command. So we have two different types of outputs. One of these are bare metal outputs. These basically have like hand implemented syscall implementations, and they're baked into the binary. Then we have Linux binaries, which actually can use all of the syscalls that exist on Linux, but they won't run in a bare metal environment. They're expecting the Linux operating system to be underneath them. So depending on where you want to run each one, you can decide. Okay, so let's actually run something on a functional simulator now, real quick. So we just looked at a very simple template program, which just moves data into the scratchpad, multiplies it, and moves the result out. Let's run that on the functional simulator. Let's go out 2 levels, and then do scripts, run spike template, and it runs right away. So you see over here that the input and output matrices are identical as expected. We can also run a slightly more complicated one where we do a much larger tiled matrix multiplication. This one over here. Again, it runs very fast because it's not actually simulating everything. It's just an ISA simulator. This script is a very simple wrapper around like calling the spike program directly with Gemmini support. So if you guys have a prior Gemmini experience, that might be how you were calling it earlier. This is just another way to call it if you want to type less. Okay. So we can also run things on the cycle accurate simulators. So let's try running something on the verilator simulation that we loaded. Let's try running the template program. So we'll do scripts, run verilator this time, .sh, and template. So you can either give it the direct path, the absolute path to the software binary that you want to run, but by default, these scripts will first look in the build directory to try to find them. And if they can't find them there, then you can give the direct path, the absolute path instead. So this is cycle accurate, so this will be a little bit slower. You can see each line coming out. It's basically doing exactly what it says. Moving data in, moving an identity matrix in, multiplying it with the identity matrix, waiting for the results to finish, then checking the results, and it all works. Okay. We won't run the -1 because it is kind of slow, but we saved the Midas log in over here in vim tutorial midas.log. Oops. So you can see it over here, over there, and you will see that it's there's a lot of like cruft in the beginning, but afterwards it's exactly the same as the Verilator implementation. You initialize your matrices, move in, multiply, move out, check the output, and the results are correct. Okay, does that make sense to everybody? Okay. You can also view the Verilog that was generated. Just open up another symlink we created. This path looks really long. You can copy it from the document we gave. But honestly, tab complete tool will get you all the way there as well. Or you can just look at my opening it. So we can see the RTL that was generated for Verilator. Yeah, and we can actually see the Verilog over here. So you know it's automatic. It's generated by a computer, so it's not very pleasant to read, but it's all in there. You can search for Gemmini in here. Let's search for module Gemmini. You can search for the CPU. Is it maybe it's called Rocket? Yeah, module Rocket Core. Oops. Okay, it's all in here. So if you want to feed that into a synthesizer or place router or whatever, you can use that. Somebody asked how you would generate waveforms. So you have to build Verilator with the debug option. Oops. Where was the example? Where did I do that? Oh, right here. So if you see, you can pass the debug option into it. That'll build a one which can generate a waveform. Then instead, you basically do run Verilator debug.sh, and then it'll generate a VCD file called waveform.vcd. And if you run the VCS, you'll get Synopsys's proprietary waveform format instead. Does that answer your question? Or okay, yeah. So I guess this took a little bit longer than I expected. Let's do the last interactive activity of the session. Let's try to add a new data type to Gemmini. So this will need a little bit more coding than just changing scalar values like before. So Gemmini is meant to allow users to create their own data types. But if they create their own data type, then they kind of need to tell us exactly how the different operations on it should be implemented, right? Because we don't necessarily know what a multiplier and addition means for your own data type. So let's open up this file called arithmetic.scala. Leave this up here for a second, and then we will implement a complex data type, a complex number data type in this file ourselves. So let's go here. Vim source main Scala Gemmini arithmetic.scala. So over here, you basically first define, if you want to create your own data type, you have to define what the raw bits of that data type are using something called a bundle, which is basically a struct, but in Chisel. So over here, we've defined a complex data type. It just has a real component and imaginary component. Just to keep things simple, we're going to use signed integers in this tutorial. In actuality, you would probably want to use floats, I guess. But like I said, doing arithmetic operations with floats is a more painful process in Chisel. Then search for tutorial in here. If we scroll up for a minute, we will see how we implemented the multiplication. So you have a self, which is the current data type that you're working on, and you have something that you another element that you want to operate. Apply this operation on. So over here for multiply, we just did the standard algorithm for how you calculate a multiplication for a complex data type. Let's do a simpler one over here. Let us implement an addition. So first we will implement the real component of the addition. So if I have self and other, and I want to find the real components of the sum of those two, how would I do that? And this is where somebody's supposed to speak up. And yeah, there's no judgment, so I'll just wait here till somebody speaks up. Even if it looks obvious, just tell me. Nobody's added two complex numbers before?
Do you just add the real component to the other real component and imaginary to the other imaginary?
Yes, exactly.
Okay.
And thank you for speaking up. Yeah. And then you add the imaginary component to the other imaginary component. So for our struct or bundle or whatever you want to call it here, oops, I said self again. Let me fix that. Dang, I'm not used to working without my MRC. Okay, you also have to give the data width. For this, we'll just set it to the maximum data width of whether self or other has the larger data width. You could choose whatever you want here. You could do max +1 to deal with the overflow or whatever. We'll just do the simplest implementation. And then we want to finally calculate a MAC here. Gemmini requires that you tell it exactly how the MAC is performed, even though it already knows how the additions and multiplications are performed, just in case you have a particular optimization for them. But we won't try to do anything fancy here. So we already have an addition and we already have a multiplication. In one line, how would we calculate the MAC? And the hint is kind of leading. So you can reuse the operations that you defined above. So don't worry if it seems obvious. Don't worry if it seems unobvious. Just, me call out a random person named Simon. Can you tell me?
Sure. You can reuse the operator you use, so you can just say self dot plus self plus m multiple.
So you can literally just copy this. So not that complicated. Thank you, Simon. He's not actually an attendee. He's one of the people who helped do this. So don't worry, I won't call you guys out. Put you guys on the spot like that. Okay, that's all. There's other operations as well. Like Gemmini wants to know exactly how you define a 0 in this, just so we can do like clock gating and stuff, or like how you do an identity operation. But we've already implemented the rest of those. Those aren't too important. How you do comparisons. We're not going to do any comparisons here, so I just set it to false. Okay. Once you have implemented it, you have to update your custom config to use it. So we'll open up Gemmini custom configs. Over here in your custom config, we've already defined the complex config here. It's just a 32-bit value with a 16-bit real and imaginary component. Just overwrite it. Just say I want to build a custom config instead of the baseline inference config. Right? It's just a one-line change. Yeah, after that, you would normally build Verilator. We're not going to do that. It'll take too long. Just run your checkpoint. Checkpoint, build complex. Sorry, tutorial, checkpoint, build complex. So that's just going to copy over a preloaded simulator that we did. When you define your own data types, unfortunately, you're going to want to run them on a Verilator, because Spike is it's just running on a CPU, and the CPU doesn't actually know, it can only use native C types. It doesn't know what your custom data types are supposed to do. So for those, you need to use Verilator or Midas or Fireson or something. Okay, let's go back, software Gemini rock tests, and rebuild the tests. Here, just since we're short on time, you can actually say build.sh bare metal.c, in which case it'll only rebuild the tests that are within the bare metal.c folder. So it won't rebuild the ImageNet models. Let's just do that to make it faster. It's actually already been installed in the checkpoint, so it finished immediately. And now the last command you need to run for this session, sorry for going a little bit over time, is we're going to run a test that we built for these complex numbers using the implementation that you, the audience, told me how to complete. So this is a very simple test. It's just going to take two diagonal matrices, both of which are just -i across the diagonal, so minus the imaginary component, and multiply them together. And it's going to check that the result is a diagonal matrix where the diagonal elements are all equal to -1, which is what you would expect. Okay, this one maybe takes a little bit. There's some printfs. That may take a little bit of time. Let me zoom out so you guys can see the structure better. Oops. Yeah. So it's just across the diagonal, there's a -i. Sorry. Give it a minute. It's very riveting stuff. And yeah, I mean, this is the last thing you need to run for this session. We'll take a break after this. So did anybody have any questions about any of it? Any of it not make sense? Any of it need more clarification? Just let me know while we wait for this to print. Need lines is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16. Okay. And then we don't have to wait for the full output matrix. But as you can see, it's just a diagonal with -1 now. So congratulations, the complex data type implementation was correct. And we'll just control C out because we don't need to wait for the rest of it. Okay, that was the first session. We went a little over time, so let's maybe take a shorter break until 11:15, and I'll see the rest of you guys at 11:15. Thanks. Or actually 1:15 in EST time, sorry. Okay, I'll see you guys soon. Okay, let's keep going. It's 11:15. So now that we've kind of gotten a better understanding of the hardware, we will step into Gemini's actual programming stack. Yeah, I think everybody is back now. Okay, so as we mentioned earlier, there are different levels at which people can program their accelerators. Gemini tries to provide access to 3 different levels, which we call the high, medium, mid, and low levels. So at the high level, you can feed in Gemini ONNX models of your neural networks, and it will run a hand-optimized implementation of each kernel that it finds in the ONNX model. ONNX can be generated by pretty much any major ML framework right now. Then there's a hand-tuned C library at the mid-level for DNNs. So this might be more helpful if you want to write your own Gemini applications rather than using ONNX. And we have different implementations for matrix multiplications, convolutions, global averaging, residual additions, whatever, lots of different kernels. And then if maybe you don't find the kernel that you want in the mid-level that we've handwritten, you might want to write your own. You can use the low level, where you're basically calling the low-level ISA directly and configuring the hardware pipeline exactly as you want. Okay, so at the high level, we have ONNX. You can run ONNX models on Gemini. ONNX is basically just a file format. For those who don't know, it's a file format that defines DNNs as a graph. And it was originally meant to be an interchange format between different neural network frameworks. So, PyTorch, TensorFlow, MXNet, all of these can create and load ONNX. I think Caffe as well, and pretty much any framework you know. And a lot of the models that you would typically want to use for image classification, or NLP, or object detection, or whatever, are already available in something called ONNX Model Zoo, which is just an online repository of these things. So most probably, you won't need to generate your own. You'll just be able to find them. So ONNX is the actual just the file format. To run these on accelerators, we use a tool called ONNX Runtime, which was originally developed by Microsoft, but we have forked it. So ONNX Runtime basically iterates over the ONNX graph, and anytime it finds a kernel that can be dispatched to an available accelerator, it will dynamically dispatch it. And if there is no such accelerator available for that kernel, it will just fall back to a CPU implementation. So it'll always run, but it might not always be performant. ONNX Runtime supports both inference and training workloads. We forked it. We have not just forked and been completely separate from them since. We've been in communication with the upstream folks, and some of our changes were actually upstreamed to the main repo. And the reason we forked it was because we wanted to do a few things that the main upstream repo was not doing at the time. We added scripts to automatically try to quantize models to int8, scripts to fuse some operations together, and a last script, kind of necessary thing, was to change the data format which tensors were stored in ONNX Runtime. So ONNX Runtime uses something called the NCHW format, where the channels are the outermost dimension. PyTorch uses a similar data format, but some other frameworks like TensorFlow use the NHWC format, where the channels are the innermost dimension. It's basically an arbitrary decision which one you choose, but oftentimes when a framework chooses one, they end up getting locked into it, unfortunately. So Gemini expects the channels to be the innermost dimension. So our fork will automatically change their format to that. Maybe in the future, if ONNX Runtime decides to support NHWC natively, we won't need this anymore. And the tool will generate a timing profile, which you can use to help debug your, to help find maybe performance bottlenecks in your application. Okay, underneath that, at the mid-level, we have a hand-tuned library of C kernels in a header file that we just call Gemini.h. This is basically what ONNX Runtime is calling. It's just calling these hand-written kernels. So we have them for matmos, residual additions, convolutions, maxpools, etc. Global averaging, other types of kernels. This library requires a description of accelerator configuration, which we wrap into a header file called Gemmini params.h, which basically just tells the library, what is the dimension of my systolic array, what data types is it operating on, etc. You could use this to write your own Gemmini applications, maybe. You could maybe write a CV application where you instantiate your own image and pass it through a convolutional filter or whatever you want to do. Things that Onyx runtime wouldn't support, maybe. The hand-tuned library uses heuristics to try to find the optimal tile sizes at runtime. But if you know at compile time what your optimal tile size is, you can also just specify that you can also specify that manually. And yeah, it assumes a certain data format. Yeah, so we have them for matmos, transpose matmos, striated matmos, convolutions for both forward and backward passes, dilated convolutions, matrix additions, different kernels. Does that make sense to everybody so far? Okay, I'm going to assume yes. Then the lowest level is what we call the low-level programming model. This is where you're calling the Gemmini ISA directly. And you should really only need to do this if you want to write your own mid-level kernels, or if you want to do some specific performance tuning that the mid-level kernels aren't doing for your own workload. So these are really just assembly instructions. You're calling the assembly instructions, but we've wrapped all of these in C defines so that you should be able to call them from directly within C without having to go down to assembly. Okay, so before we go into the different commands that are in the low-level model, it's useful, I think, to understand exactly what the programming model is here. This is a base. So Gemmini is basically programmed using custom RISC-V instructions through something called the ROC interface, which is basically just an accelerator interface for that was developed for a rocket chip. So on the right, we have a custom RISC-V instruction, the formatting of which can be fed into Gemmini. So these instructions are interspersed between ordinary CPU instructions, right? You don't need to save your Gemmini code in a specific code region and have Gemmini fetch that directly. You intersperse these commands freely through your own CPU commands. Gemmini doesn't fetch its own instructions, doesn't have an instruction fetcher. The CPU just, whenever it runs across these custom instructions, it will check the opcode to find which accelerator it needs to go to, and just dispatch it to that accelerator. And then because the CPU doesn't actually know what this custom instruction is supposed to do, it just immediately continues execution. And you have to synchronize with fences if you want any synchronization. So here's just a high-level model of what I said. You have a CPU, and it's feeding commands with RS1, RS2 to Gemmini. Gemmini is only responding with a single bit signal, telling the CPU whether it's busy or not. And whenever Gemmini completes the instruction, this busy bit will go down to low, and then the CPU, if it's fencing, will continue execution, assume that it's finished all the commands it has fed it so far. Okay, so I got some pushback earlier about our definition here. Maybe we can revise what we're calling it, but up till now we've referred to Gemmini as the decoupled access execute architecture. So we have three different types of instructions. We have three different access execute pipelines, I guess. One is for load instructions, which move data from main memory into the scratchpad. One is for execute instructions, which take data that is already in the scratchpad and write it back into the scratchpad. And we have store instructions, which do the opposite of the load. Kind of intuitive. And these three different types of instructions basically match how the accelerator is actually implemented with these different pipelines. So we already saw this example earlier. We can look at it again, just briefly to get a firmer understanding of what we mean by these examples. So let me go here. So this is a template program that was meant to help people get started with their own low-level programs. Sorry, just trying to change the size. Okay, and it's basically calling low-level commands, right? Configuring the pipelines, moving in, doing matmos, moving out, then fencing at the very end until the results come back. So kind of intuitive.
Quick question here. So it looks like you have 3 different kinds of moving instructions. Is it because that you have 3 different queues, moving 1, 2, 3?
That's actually in a future slide. I'll talk about the difference between them, but they're all in the same queue. They all share the same queue.
I see, got it.
They're not meant to be. Yeah, they're all in the same queue. Mm-hmm. Okay, and the last thing you need to understand if you want to write your own Gemini programs is, it's how the local memory is actually accessed and indexed. The local memory needs to be explicitly managed by the programmer. We say it's row addressed. I'm not sure what the official terminology is. Basically, every row of the scratchpad has as many elements as the systolic array has along its horizontal dimension. So if you have a systolic array with 2 PEs, each row of the scratchpad has 2 values. And then we have an accumulator, which is just like the scratchpad, except that it's wider, because you might need a wider data type to accumulate your partial sums into. And they're both the scratchpad and the accumulator are part of the same memory space. It's just that if you want to access the accumulator and write results to the accumulator or read results from the accumulator, you set the very first bit of the 32-bit scratchpad address to 1, and then you're accessing the accumulator. If it's 0, you're accessing the scratchpad. Okay, does that make sense? Okay, so now that we understand the programming model, what it's actually doing in hardware and how the memory is meant to be managed, let's go through the pipelines. So yeah, Gemini actually has 3 identical move-in instructions: move-in 1, move-in 2, move-in 3. They're actually identical, but each one has its own config registers, right? So move-in 1 and move-in 2, you can set different strides for them. The reason we did this was because sometimes when you're doing like let's say a convolution, you might have different strides that you need, or different scalar multipliers that you need for your inputs, weights, and biases. So this just lets you configure different configs for each one of those without you having to keep switching back and forth. So these instructions are kind of low granularity. You're meant to move basically submatrices that are the same dimensions as a systolic array. That's what the DIM says, from main memory into the scratchpad. You also need to configure this. I've just given some of the config options, just the most important. It's not too complicated, I think. You have the stride in bytes between different rows of the submatrix. You have a scalar value, because Gemini actually can do matrix multiply scales matrix scalar multiplications while the data is being streamed into the scratchpad. And you have the ID, so whether you want to do number 1, number 2, or number 3. Okay, does that answer your question about the difference between them?
Yes, so basically the configuration is different, but actually the queue is the basically same queue, right? Right. Okay.
Yeah, functionality is same, queue is same. It's just a config.
Yeah, great.
Cool. Okay, so we just have a simple diagram here. Let's say you have a large 2D matrix in main memory. You want to move the top submatrix into your scratchpad. So you configure what the stride is between these 2 different rows, and then they get moved into the scratchpad. Okay, and most of this stuff is actually in the Gemini README as well. So if you want to come back to it later, you can also read it there. But we will also publish these slides in video. Okay, the execute pipeline actually uses 2 different instructions to do like dot products and matrix multiplications. First, there's a preload instruction where you preload stationary data into your spatial array. So for example, if you have a weight stationary data flow, you might want to preload weights into it. If you have output stationary, you would want to preload biases or maybe just zeros into it. Afterwards, we have another compute instruction, which is actually responsible for feeding data into the spatial unit once the stationary data has been preloaded. You might want to feed in maybe you preloaded your weights, now you're feeding in inputs into it and getting outputs out of it. And it also, you also have to configure that pipeline if you want to use it. You have to say which data flow you want to use, for example, output stationary, input stationary. You can choose which activation function you want to use for the output stationary data flow. Whether you want to transpose any of the inputs, and which stride you want to access data at within the scratchpad. Because for certain types of workloads, it can be useful to actually perform mathematics with non-contiguous rows of the scratchpad. Okay, then there's the store pipeline, which is very similar to the load pipeline, just the opposite. It stores the submatrices of about the same granularity into main memory. So it has some special caveats. For the weight stationary data flow, the activation functions are actually applied as the data is being read out of the partial accumulators. And max pooling also occurs over here as it's being read out of the partial accumulators. And the reason we can't do that in a systolic array is because with the weight stationary data flow, you don't actually know what the final result is until you've done all of your accumulations. Okay. And yeah, the configs are not that different than the load, except that you have options also for the activation and the pooling. Okay, so the last in part, I guess, to understanding the ISA is the distinction between what we call primitive and complex instructions. This is not a very like a formal distinction. This is more of an informal distinction that we have between them, and I'll explain what we mean by those. So the primitive instructions are the ones that I've implemented right now. So like move-ins, preloads, computes, they have a small granularity. They operate on submatrices the same size as the spatial unit itself, and they require the programmer to explicitly manage the scratchpad. Then we have, so in the mid-level programming stack, where there are all these handwritten kernels, those kernels are really just calling these primitive instructions and composing them into loops, right? So if you want to do a convolution, you just do a lot of dot products on different parts of the data. However, we found that we could actually hard code a lot of these loop structures inside the loop unroller that we talked about in the first session. It's not necessary to do this. You can do the same thing with the primitive instructions, but it can be useful for performance, basically, because then you kind of activate like dynamic scheduling. Without these kinds of instructions, you may have to do you may have to do like software pipelining or loop unrolling or more tedious optimizations to get the same level of overlap and performance. Yeah, and these are optional. So if you don't like these complex instructions, you don't have to use them. Yeah. So here's an example. This kind of looks complicated, but it's just a tiled matrix multiplication. You have your main memory tiles here, your scratchpad tiles over here, and you're just calling a lot of primitive instructions inside of the loop body. So with the complex instructions, you can take all of this, and it's just one instruction. So now you're just doing you've collapsed your scratchpad tiles basically into one instruction. That's all it is. Okay, does that make sense to everybody? Okay, going to assume so. Yeah, so let's do a few interactive activities now to try to like move across this programming stack to help make it more clear. Firstly, let's try to visualize and run ONNX models. On your personal laptop, try to go to this link and download it. So the reason why I have to do it on our personal laptop is because we're going to visualize it, and we weren't sure how to actually set up the UI on these AWS instances. So you'll have to humor us. Yeah, and Dima has posted the link in the chat if you want to go to it quickly. Let me come here. So it got downloaded over here. Oh, it's being downloaded. It's a 30 megabyte file. Okay, then go to this nifty little website called netron.app. Okay. So, you could also do this with a standalone application, obviously, but we're not assuming that any of you guys have downloaded one. So just come to this nifty little website by this guy. And then you can just load your Onyx model, just drag and drop it into here. And then you can see the whole model, right? So there's nothing unique or special about these. You can see every operation that's running. So we've quantized this one ahead of time, so you can see the quantization paths. But there's convolutions, max pools. You can see the residual addition if you're familiar with ResNet 50. It has branches, so you can see the branches in the diagram and how the branches get merged back together with additions. And yeah, you can see all of the different operators. It's kind of a large model, but give me a second. Yeah, at the very end, the average pool, gem, and the softmax. And then the result is written out here. Yeah, and Simon mentioned in the chat that we also have some other Onyx models that we have pre-quantized, so feel free to go there if you want to in the future. Okay. If nobody asks me anything, I'm going to assume everybody is doing fine. Let me know if I'm going too fast. Now that we understand the model, let's try to run it. So unfortunately, we do not yet have the same convenient scripts that we have for running the bare metal tests. Running the Onyx models is a little, you need to do a little bit more typing. So first, let's just preload the Onyx inference libraries. In actuality, you would have to build these yourself from source, but we don't have the time for that. So just come over here, do a tutorial checkpoint, build Onyx inference. I'll leave this up for a minute so everybody can type it. Build Onyx inference. Okay, so let's just give it a minute to copy everything over. Okay, and if you want to read up more on this, this is also in the Onyx runtime docs if you forget these commands and you don't want to go through these slides again. Okay, so our Onyx runtime port is a sub module of the ArchiTub repo. So let's try to go to that path. Just go to software, Onyx runtime -RISC-V. And then within there, go to the custom runners that we created for our own accelerator in a systolic runner / ImageNet runner. Okay, let me do that as well. See software, Onyx runtime RISC-V, systolic runner, ImageNet runner. Oops. Okay. So earlier we had the run spike script for the bare metal tests. We don't have that for the spike test, but it's basically the same command. I'm just not using a thin wrapper anymore. So you call spike, which is our functional simulator, directly on telling it that you want to use the Gemmini module, and you call the runner, which is called ORT test. So this PK is a proxy kernel. This is basically implementing some features of the Linux OS, not the whole thing, obviously, but some features which Onyx runtime is expecting. Let's first just run it with the -H option, just to demystify it. So spike extension equals to Gemmini, PK, which is a proxy kernel, which is our mini Linux, I guess you could think, although much more simpler than that. ORT test. ORT means Onyx runtime. The test means that this is like inference, basically, the test pass. And then let's just run it with -H. And you can see all the options you have here. So if there's options you don't understand over here, they're all explained over here. Then we'll actually run the module. We'll run an inference pass on ResNet 50 on an image of a dog. So over here with this -m, we're just saying which model we want to run. We want to run the ResNet 50 that we've quantized using other scripts that are in this repo. We want to run it on the image of the dog. This P is a pre-processing pass, basically based on which module this network came from. It may need to do some pre-processing. Like there's other options for other frameworks other than Caffe. -x tells you which data flow you want to run with. 0 means run it on the CPU. 1 means run it with a output stationary. 2 means run it with wait stationary. And this -o is what optimizations do I want to do. So we want every optimization. That's why we set it to 99. If you don't want to type all that, you can just go back to the Gemmini repo, and there's a command there, tutorial run onyx inference.sh, which just does this. So I will just do that. I will just run tutorial run onyx inference.sh. Let's just give it a minute to run. It's running a full model, so it'll be a little bit slower. Zoom in a bit. So does anybody have any questions while we wait for this? So, you can see the dimensions of the image that we loaded in. Just printing the different operations that it's running, pooling and conf and add. Nothing very complicated, I guess. ResNet 50, maybe not most of you, but some of you are probably already pretty familiar with it. Just going through the network. Yeah, and now we see our inference, our predictions. So it was an image of a dog, and it thinks it's probably either a Rottweiler or a Labrador Retriever, or maybe like 8% a Great Dane. So if you open up the doc that we posted at the beginning with all of the commands, you can actually see the image of the dog in there. Down here, so it's cute. I don't think that's a Rottweiler, but anyway, that's what the model thought. Okay, you can also run training. Training runs much more slowly, unfortunately. But you can pre-build the checkpoint for Onyx training this time. Let's do that as well. Tutorials, checkpoints, build Onyx training. And this is similar to the inference, except that here you're going to go into the trainer rather than the runner. The runner is for inference, the trainer is for training. Binary name is slightly different, but the options are pretty similar. Right? You have your model name again. You have to give it a little bit more information, like the actual, like a list of the actual images that you're looking at. We just kept it very simple, just one step, batch size of 2, which obviously isn't an optimal batch size to train ResNet 50, but it suffices. Any options, questions? Somebody asked if the clock cycles we're getting are consistent with Verilator No, like the spike is just functional. It doesn't make any guarantees with respect to performance. In fact, I think it assumes that every instruction takes one cycle, which obviously isn't accurate. So just since Gemmini operates at a higher granularity than the CPU, it will always look much faster than the CPU. Okay, and then we can run this command, run Onyx training. So this one is much slower. Yeah, so this one is actually very slow. We don't really have time to run it. You can see the beginning, right? So it's getting your list of files, preparing to run them. It's going to do a little bit of pre-processing, look at the labels. But we are not going to wait for this whole thing to finish. So just a Control C out of it. And then you can see a file called train1.log. Actually, where was that file? I should have put the name of the location of the file. Let's just run train. Okay, it's within the ImageNet trainer. And we can just see what the log is here very quickly. This is what we would have run if we had waited for it to finish running. So yeah, there's a pre-processing pass where it has to convert everything to our data format, IISWC. And at the very end, you can see after it's called the forward and backward operations, it has the loss somewhere here. Yeah, over here. Yeah, so this was just one step with a batch size of 2. It's obviously the network isn't trained yet, but if you keep going, it will be eventually. Okay, does that make sense to everybody? Okay, and then for the last thing and then we will try to visualize the Onyx runtime trace from our laptop. So again, try to download this URL. Just going to click on it. This is just a whole thing. I am just going to, I already have it saved somewhere. Yeah, so I already have it saved. So you can actually load this in Chrome if you have Chrome. So just go to Chrome//tracing, and then you can load in the network. So obviously you can download a program which is designed specifically for this as well, but if you don't, Chrome is very convenient. So initially there's a lot of just setup. That's kind of slow. Not much we can do about that. And then you can zoom in to see the model running itself, and you can see the different kernels, right? You can see the convolutions, mostly just convolutions. You can see average pooling at the end, the final classifier layer, etc. Okay, now any questions? Yeah, so Franklin asked about how long the script took. On Spike, it took about an hour, but that was just for one iteration. So it's kind of slow right now, to be honest. We haven't been able to run full end-to-end training yet. Just basically individual iterations, or we've run like 2 or 3 iterations at a time. But on FireSim, it would be faster. Yeah, so this is just a simulation, to be clear, and there's a lot of CPU preprocessing. If you did it end-to-end on FireSim, it would be faster. Okay. Afterwards, one of our students, Simon, wrote scripts that you can actually use to inspect these traces from the command line. So they are underneath Onyx runtime. Let's quickly go to those. Let me just copy paste these. Oops. Gemmini software. Oh, the path was wrong. Okay, that's okay. Time systolic runner, Internet runner. Yeah, and then we won't go through all of these, but we can get summaries basically of the trace and of how long it ran. So I think I have to go to tools. Okay, so we can see for each of the traces, whether they ran on the CPU or the accelerator. By default, our script, our quantization script, will run the final gem layer in FP32 on the CPU, because for some networks, the final classification layer can be kind of sensitive to quantization. But if you hand quantize it, you could run that on the accelerator as well. You can see how long different operations take. You have different. You can see, the layer-wise statistics. For every layer, how long it took, etc. And there's different options here. You're just changing the stash operation here. Okay, let's go back. Okay, let's do one last interactive activity, and then we can take another short break. So Onyx runtime is how we do, I guess, the high-level programming. What if you actually wanted to step down to the ISA yourself? So we'll do a very particular optimization for the first layer of ResNet 50 using the low-level ISA, an optimization which doesn't exist right now in the kernel implementation, mid-level implementation. So assuming most of you guys have seen what a convolution is before, just in case you haven't, you have a number of filters applied across an input to produce, an output. Gemmini has to store these 3D inputs in a 2D format within its 2D scratchpad. So it stores them, as I said, numerous times in the NHWC format. You have all the pixels in the first row side by side, second row, third row, and the innermost channel is the dimension is the input channels. So we can compute convolutions with matrix vector multiplications. Then Gemmini actually does them with matmos, so with another axis of a parallelization. But just to keep it simple for this tutorial, we'll just talk about matrix vectorizations. And you can iterate over them over different pixels, reducing them across the weights and accumulating the result into the output. Right. So not that complicated. Or if you need more, if you don't understand, just let me know. So when the input channels are large, this is fine, right? Let's say you have an 8-byte systolic array and then 8 input channels. You can keep the entire systolic array utilized as you feed different vectors into it. But for the very first channel of ResNet 50, the input channels are small. See, we only have 3 over here. In that case, the shared dimension over which we do the dot products is much smaller. It's only 3 elements wide rather than 8 elements wide. So a large portion of your spatial array, your matmul unit, might be left unutilized. And this is a persistent problem that a lot of different accelerators have to deal with. For example, NVIDIA has specific different features just for the first layer that don't apply to the other layers, just to deal with these troublesome layers where the input channels are low. And as you know, they can be a significant drain on performance after a while. So here's an insight though. We could duplicate the data in the scratchpad and reduce across not just input channels, but the input channels and 2 of the kernel columns at the same time. Right. So in this case, your shared dimension is actually 2 different dimensions of the original 3D image that have been multiplied together. And now your utilization is 6 out of 8, for example. So it's much better, right? And this is also what some other accelerators do. So let's try to implement that ourselves using the low-level ISA, assuming you have an implementation where that doesn't exist. So we'll just change 3 lines to do that. So let's go out again. Yeah, let's go here. Software, Gemmini Rock tests. Let's open up Gemmini.h. And let's search for this word tutorial. Okay, so I have a dummy implementation of a conf here. We will try to optimize it. So K is basically the shared dimension over our matrix multiplications. And right now K is too small because K by default is the input channels. And maybe K is just 3. So let's say we want to reduce over both 3 channels and 3 input columns simultaneously. So if we want to reduce over 3 input columns, what would we multiply K with? So originally K is just representing 1 input column. Now we want to represent 3. Does anybody have an idea? It might seem obvious. It's fine if it does. It might not be obvious. It's fine if it isn't. I'll just wait a minute to see.
I guess you want 3 times K there.
Yeah,
right?
exactly. Yeah. Yeah, so these hints might be kind of leading, but yeah. Right. So afterwards you're iterating over your convolution, right? Originally the kernel columns were not being parallelized over. You were just going over them one by one, but now you're going over 3 of them at the same time. So this might also seem obvious. What are you going to increment them by?
The same old 3.
Yes. Yeah. And then there's just one more place where K comes up. We're actually doing the matmul. And yeah, I won't force you guys to say it again. Once again, originally over here, we're just reducing over the kernel channels, but we want to reduce over the kernel channels times 3 of the kernel columns at the same time. So we'll just multiply it by 3. That's all, right? So we just changed 3 lines. Pretty simple. I got a question. Does conv-tiled auto function include this, or conv-tiled auto is more optimized than this? This was more of a dummy implementation to make it simpler. This, for example, doesn't support padding or certain optimizations that the other implementations do. Anyway, then we can build the output. We can give it a minute to finish building our new implementation. So just out of curiosity, how many? So sometimes in the Docker image, you get these errors. Just ignore them. We don't know why it's saying it's errored. It's as far as we can tell, it's building everything fine. Just seems to be something with Docker. So just out of curiosity, how many of you were already familiar with this like first layer optimization? Like it's not like very hard to think of, but I think unless you've run into it yourself, maybe you don't run across it. Like, has anybody implemented this before, or had to implement it, or dealt with difficult tensor shapes like that before? Just give it a minute. Okay, it's done. Let's go back out. We want to use the baseline config again because we changed the config earlier. We're using the complex config. Let's change it back to the baseline config and rebuild Spike. That might also take a minute or two. Wait, we shouldn't need this last build, I think. So is everybody following along okay? Okay, maybe we're running out of time for this session. So I can kind of skip ahead to the end. You can run Spike on the first layer, and it will basically tell you that your output is correct, right? Yeah, let's see, seems to have finished. Let's see. Or no, sorry, what was the name of it? Conf first layer. Yeah, so it returned the correct results. So with Spike, you can check whether or not the results are correct. But you can't get accurate performance numbers. But when we actually ran these on Verilator, what we found was that with this first, just changing these 3 lines, on the first layer, you get like a 52% speed up. So it's not exactly 3x because there is an overhead to doing this. You are moving more data in between. And also because the implementation we gave for this tutorial was very simple. You wouldn't really need to like unroll loops and do stuff like that to get better performance. But yeah, so you can see how you can use the low-level ISA maybe to do special performance tuning for special types of shapes that are not supported in the mid-level library. Let's maybe take another quick break until 12:10 for me. I think that's 3:10 in Eastern time. So for about 7 minutes. And in the meantime, feel free to message us if you have any questions, or just grab a drink of water. Thanks. I'll see everybody soon. And at 3:10 Eastern time. Okay, maybe we'll wait a few more seconds. Okay, let's get started again. We're maybe 10 minutes behind schedule, but it should be fine. We'll do our last session here about performance profiling on Gemini before we do our very quick parting thoughts. Okay, so Gemini basically has two different types of performance counters if you want to do profiling. There are counters that exist on the SOC. So these counters, they're actually implemented in RTL. If you access these, you could theoretically affect, power performance area, but they'll actually be on the actual chip. So if you're taping out, they might be useful. Then there are counters which exist only in simulation. So these are generated during FireSim simulations. So we've provided some logs already because we're not going to run FireSim in this tutorial. They don't affect the performance area power, but when you tape out and hold the actual chip in your hands, you won't have access to them anymore. So they're only useful before then. So the SOC counters are configurable. The architect can decide how many counters to add at elaboration time. They can add up to 8, I believe, or up to 7 counters. The ISA for them is also pretty simple. You can read them, you can reset them, or you can save all of the counter values to a snapshot. If you want to save them all at an instantaneous moment in time and then read them out one by one. So some of these counters are monotonic. They just always go up by 1, basically. Maybe incremental consecutive would be a better word. For example, TLB hits or misses. They're either going to stay the same or they're going to go up by 1. Others are non-monotonic. They can go up or down, or maybe they can go up by values greater than 1, like 10 or 20 or whatever. So for example, we have a counter for the instantaneous utilization of the reservation station between different types of instruction queues. We had used that a while back to help us calculate how much overlap we were getting between different types of instructions. That can go up or down. Counters basically begin when your program begins in a disabled state. Disabled counters, aren't really counting anything, and the programmer has to decide which, quote unquote, counter code to enable each counter with. So counter code is just a signal, basically. So maybe you want your first counter to measure TLB hits. So you configure it, and then it will be tied to the TLB, and it will be monitoring its hits. Yeah, and you can tie different ones to different types of signals from like lists that we pre-generated. And if people here would like us to add more signals to that list, we would be happy to. It's not difficult. We could do it in like a few lines of code. The simulation counters only exist in FireSim because we use FireSim features to get them. Over here as well, we have counters, logs for counters which just monotonically go up by 1. Logs for counters which can go up or down. And a special log for the DRAM controller or the last level cache if you want memory stats for that. And I've already mentioned what FireSim is, but it's basically you're making your simulations run much faster on FPGA in the cloud. So it's like it's much faster than Verilator. So we have some of the counters that we have here. We have signals right now for TLB hit miss rates and hit rates, the latency of different Gemini DMA requests, the bandwidth of different Gemini DMAs, instantaneous like stats for the reservation station. Counters are like 1-bit counters are meant to help us kind of try to estimate how much overlap we're getting between execute, load, and store instructions. Counters that try to figure out why the DMA is blocked. Is it blocked because the TLB isn't responding and it would have been ready to issue an instruction otherwise? Or maybe it's blocked because the main memory system isn't ready. So we say that's blocked on the tie-link port because tie-link is the interface. It's just like the name of an interface that we use to access the L2 in main memory. So we count how many cycles the DMA would have been ready to issue, but the main memory system did not have enough, was not accepting requests at that time. And for the simulation counters, we have all of these, and also LLC memory stats for the last level cache that you can't get through the Gemmini SOC counters. Okay, wait, so did that make sense to everybody? Does anybody have any questions? And yeah, I mean, our process for adding new counters is basically, oh, we need to make something run better. I would really like if I had this counter, so we add it. So if anybody has their own ideas, just email us. It's not hard for us to add these. Okay, let's do a few interactive activities now. So we published a description of Gemmini in a paper in DAC that will be coming out, I think, this December. And we had a few case studies there. So in the next few interactive activities, we'll try to not replicate the full results because that would be tedious, but to partially replicate them or gain more insight into those results using these different logs and counters. So let's look at Gemmini's simulation logs first. We have some of these logs saved from a batch for ResNet 50 inference run on ResNet 50. So we have a log here for the monotonic counters. Oops, let me go back. So let me leave this open for a minute and you can open this up with Vim or Nano or whichever, or Less or Cat or actually don't use Less. Less doesn't work well on Docker, but use Vim or Nano. Okay, I'm assuming people have opened it. If not, let me know. Wait, it was the path again. Oh. Net 50 counter.log. Okay, so let's go to the beginning. So it tells you every cycle, like which cycle it's at. You can change in FireSim the frequency at which to print these. And for each cycle, it basically gives you the value of each counter. So initially, they're all 0 because the system is just starting up and nothing has really run yet. But later on, towards when you go to the end of the file, you can see how many TLB hits you had in total, how many other counters, how many counters was the DM active for, how much time did you spend pooling, how much time did you spend just flushing the execute the systolic array, which can sometimes be a problem for output stationary data flows, for different components of our accelerator. Okay, so not that much to say there. Does that make sense to everybody? Okay. Oh. I thought somebody was about to say something, but okay. We have another one for the printfs. I've kind of renamed them here just to make it faster to type, but I also have what the file name will be in ResNet 50 over here. So these are the non-monotonic ones. They can go up or down, or if they go up, they can go up by more than one at a time. And they're basically just implemented as like Verilog printfs at like a certain frequency. So again, initially everything is 0. There's way fewer of these than the others. You have counters for that are trying to estimate the latency of write and read DMA operations and the total number of bytes sent and received, and values for the reservation station, etc. Again, they start off as 0. You can go to the end, and you can see that the DMA values have gone up a lot, whereas the reservation station ones are back to 0 because all the reservation stations are now empty. And you can also see how many of these is incomplete means unissued here. So you can kind of track how much your dependencies are slowing you down. whether you're stalling on dependencies a lot, because if you have a very large number of instructions in your reservation station which are not ready to issue, then these values will be high. So, yeah. Okay. And then we have the last one, change from Firestone for the memory sets. So this is parts of the DRAM controller. It is a CSV file. The other ones are, just text dumps. This one is a CSV file. Sorry, which maybe makes it harder to eyeball, but it also does make it easier to just feed into like a pandas or something like that. Let's open up memory stats.csv. You can see the CSV headers on top and the values below. So the value that is most useful to me here is the give me a sec, right over here. No, wait. Total reads. Okay, the total reads, because the total reads to the LLC tells you, to the L3 tells you how many misses you've had in the L2, right? You never read from the last level cache or the DRAM unless you've missed on the L2. There's other stuff here for DRAM like rank, power, CASR. To be honest, I don't know much about DRAM, so not that like familiar with those counters. But if you do want more insight into how into your DRAM performance, you can use those as well. Yeah, so if you have pandas or whatever, it's very convenient. Okay, so that's just looking through the logs to kind of get a sense of how they look like. Let's try to actually maybe do something with them. Let's try to partially represent or replicate the result we got from our publication in DEC. So is everybody okay so far? Okay, so so one case study we did previously was to try to play around with the TLB hierarchy and see how it affected performance. So with Gemmini, you can produce a multi-level TLB hierarchy. The CPU and the accelerator have their own private TLBs, but they can share a TLB at the L2 level. And you can also use those logs I mentioned earlier. You can plot them with pandas or matplotlib and get different like sliding windows of like your TLB hit or miss rate latency. You can see it's very bumpy, cyclical. I'm not sure what the right word is. Goes up and down a lot, but towards the end, the TLB miss rate can actually get pretty bad, like up to 30% for a ResNet 50 run. This might be because the operations are tiled, so the memory access can actually be pretty scattered. So we tried plotting basically the effect of different TLB entries on performance, and we also experimented with low-cost optimizations, like a single entry L0 TLB to filter out consecutive TLB requests to the same page and return results instantaneously rather than after a cycle. And we found in general that the small private TLB was much more impactful for performance. Adding just a dozen private TLB entries is much more important than adding maybe hundreds of shared TLB entries, just due to the latencies of accessing it. But with the low-cost optimization, the results were flattened a lot more to where it made a very big impact on performance, just saving that one cycle. So we can go across the cross section of this graph. We won't go over all of these. You can go across the cross section down the middle, the diagonal, by looking at some logs, right? So I have some logs over here. I'll leave this up for a minute so people can open the first one. So it's in tutorial TLB, a local four TLBs for entries for the private TLB and 0 entries for the shared one, all the way up to 16 and 512. So let's see, tutorial. TLB, local 4, shared 0. If you go to the very end, you can search for RDMA TLB wait cycles. So this is telling you how many cycles your read DMA was stalling just because it was waiting for the TLB. And if it wasn't for that, it would have been able to issue another request. So you can see it spent about 7 million cycles in total. And then we can go through the other ones as well. Just search for that final value at the very end. This one had to wait way fewer, just about 2 million cycles. So your rate was really reduced. And we can plot these, and you can see that after a while you start to get diminishing gains. So nothing too surprising here, but just a demonstration of how you can use the TLB counters in the FireSim simulation logs and where to look to try to find this data. Does that make sense to everybody? Okay, we can try maybe also more interactive activity where we'll actually try using the SOC counters this time, not the FireSim counters, but the SOC counters to investigate layer bottlenecks. So we'll do a little bit of coding again, and you guys will help me again. So for this one, there's actually a brief setup that's necessary. There was a last-minute issue, so if you guys could run these instructions and git pull within the Gemmini rock tests repo, that would be useful. I will do it as well. This will be our last interactive activity. So let me go to software, Gemmini rock tests, check out IISWC tutorial, and then just git pull. Okay. Okay. Cool. So for this, we'll be doing another case study where we'll be trying to figure out, what is the optimal memory partitioning scheme in single and dual core data parallel inference workloads. That's a mouthful. So we have local private scratch pads for our accelerators, but they can also share a larger L2 cache with each other and with the host CPUs. So if we had, like an extra 1 megabyte of memory, for example, of SRAMs, where would we want to provision them? Would we want to add them to the shared L2 cache or the scratch pad and accumulator? Would this depend on the layer composition? Would this, change between single and dual core cases? Let's see. So, in the single core case, we found that increasing the size of the private scratch pad was much more helpful. And mainly because it made a big positive impact on the convolutions. For matrix multiplications and residual additions, it didn't have a very large positive or negative impact on performance, but increasing the scratch pad size is very useful for the comms which have like such high reuse. And so increasing the size of the scratch pad was more effective for overall performance. For the dual core case, we found that increasing the size of the shared L2 was much more helpful, but it wasn't because it helped with the comms, which are actually where most of the ops in a ResNet 50 inference go. So even in the dual core case, the comms did better with the bigger private scratch pad, where they could exploit reuse more effectively. But the issue, and the math models didn't really care much one way or another. The real issue was the residual additions. Residual additions have a low memory reuse, almost no memory reuse, in fact. And on top of that, there is sometimes a long delay between the output of one layer and when it's going to be added to the output of another layer in the residual addition, if you remember those long branches that we saw in the Onyx model. And so when you increase L2 contention through the dual core case, you increase the chance that you are going to be evicting results from the evicting layer outputs that would have been used later on in a residual addition. And the fact that they perform much better with the bigger L2 makes up for the fact that the convolutions that are preferred the big scratchpad. So let's see maybe how we could add SOC counters to try to replicate this result, right? So let's open up this program, this file. We are going to take just a slice of several layers out of ResNet 50, basically a few convolutions followed by a residual addition, and we're going to try to gain more insight into the residual addition layer performance. So if you guys open up this file, so I will go and open up the file as well. Okay, and then search for tutorial in big capital letters. So we're going to do two things here. First, we want to configure two different counters for demonstration purposes. One which will tell us the total number of bytes read by the read DMA, and one which will tell us how many cycles did the L2 stall for, did the read DMA stall for, because the L2 was just so busy with all these like evictions and stuff. So you can open up this file called Gemmini counter.h, which has all of the different counter values, like the counter codes for the different signals. Give me a second. I'm very inefficient without my MRC. So let's try to look at this counter file and find the codes for these two different values. So to get the total bytes read, we can we can search for our DMA, and then that's the read DMA, keep searching, and then we can get the total number of bytes received. So let's copy this result, go down here. And let's say we want to set up one counter to calculate this value. Now we have up to 8 counters. We get to decide which counter we want to be reading this signal. Does anybody have a preference? I won't continue till somebody gives me a number between 0 and 8. Okay, I guess I'm not that strong. I will continue. let's just use the counter number 0 to get the bytes received. Afterwards, we want to see how often it's stalled, looking for the L2. Let's just keep searching through our DMA. And we can get what we call the tile link wait cycles here. So that's the number of cycles that it was waiting for tile link to be ready. And tile link is, as I mentioned, the interface through which we read L2, through which we access L2. So is everybody following along okay so far? So I have to choose a number. Let's say counter number 3 will read the tile link wait cycles. It could be any number. Now we have to read these values from the counters that we gave earlier. So if we want the total bytes read, we tied that to counter 0. So which number should I give here? Which counter should I read from?
Zero.
Thank you. Yes. And over here.
Three.
Yes. Thank you. 3 came up a lot in this tutorial, actually. Number 3. Okay. And that's it, right? That's all you need to do. We reset our counters here. just to make them all 0 again. So it's not polluted with the past layers. And we configured them, and then we read the results out here. Just to reemphasize, this is just a slice of ResNet 50. We took layers 6 through 8, which define the branch point where a residual addition begins to branch off, and the final merge point at the end. So again, you would have to run this on Firesim or Verilator to get the full performance. Running this on Verilator would probably take too long because these layers can be kind of large. We'll just run on Spike here. So let's go out here again and run Spike profile ResAd tutorial. Scripts, run Spike profile ResAd tutorial. Oh, sorry, I forgot to build. Let me build my changes. So that's what this line is for. It's build.sh. Let's just give it a minute. Yeah, ignore those errors. That's just Docker complaining for some reason. That doesn't happen when you're building outside of Docker, and even in Docker, like the binary is built. They just complain about std out for some reason. I don't know why. Just give them another minute. Just a little bit longer. Yeah, ideally to be running this through if you want to build Verilator and everything, you'd be running this through a more powerful server than the ones that we gave you guys. Okay, great. As I said, ignore the errors. They're lying. It worked. Okay. And yeah, let's run the application now. So we'll just run this on Spike. Just to check that we're not making a mistake. But again, the numbers you get from Spike really don't mean anything, like performance numbers, counters, cycle numbers. Spike is just for checking functional correctness. I think the default implementation is to just increment these by 1 or something every few cycles. So you can't get accurate performance numbers from there, but you can run these on Firesim or Verilator later on if you want. So here's a run from Firesim. What we find is that, when we run in the dual core case, the residual additions are slower, right? Like 65% slower, at least this one residual addition for this one particular layer. RDMA bandwidth goes down a lot. And the main reason is just because it's stalling for the L2 a lot more now, which kind of confirms what we said earlier. There's much more contention over the L2, because of all these evictions that are occurring due to layer outputs that have been output several layers ago having been evicted by this point. So they have to be pulled back in from DRAM. Okay, so those are all of our main sessions. We just have like 2 or 3 slides on just quick parting thoughts. Did anybody have any questions about the last session? Yeah, and again, if you're hacking on the system and you come across a signal that you want to be able to tie to the counters, just let us know. We can do that. Okay. So in summary, Gemmini is, we built Gemmini to try to be a full system, full stack DNN accelerator evaluation platform. You can tune different components of a full SoC, and you can use different levels of the programming stack for different use cases, and you can try to see how they impact your overall performance. So I said future plans. This is more like ongoing work. So one thing we'd like to use maybe Gemmini for is to try to figure out ideal programming models for DNN accelerators. The primitives I gave earlier were kind of designed in an ad hoc style, right? We were just adding more and more features as we came across them, but maybe they weren't exactly the right primitives. So how could we, design a more principled programming interface for these accelerators at this like low level? And maybe how could we better trade off the programmability, flexibility, and efficiency of them? So mostly we've, it's in the name Gemmini, we've mostly been focusing on gems, or at least operations which can be mapped to gems. But that's only, a small subset of maybe not a small subset, maybe that's a larger subset, maybe that's a large subset of the kernels that people try to accelerate, but it's not the be all end all. And there's a lot more out there. So we'd like to try to incorporate non-gem spatial arrays into here. Then there's just, continuing dev work. The training workloads are not very optimized right now. There's a lot of kernels like batch norms, for example, which Gemmini doesn't have hardware to support right now. And those run on the CPU. Batch norms, max pooling where you need the indices. There's the softmax, for example. Those run on the CPU right now because Gemmini doesn't have the averaging functionality that it needs for them. So we'd like to tune it better for those types of workloads. And we have an undergrad working on power area improvements. We'd like to keep pushing along that front. Some of the new features we've added may have increased area, especially for the loop unroller. So we'd like to get that back down. And thanks for attending. So this is these are the people who participated in in making these slides and getting all of this set up. I couldn't have done all of this without them. You probably got an email from Dima, and maybe you interacted with Dima and Simon in the chat. And Avi is somebody else who was helping us as well. Yeah, and thanks for attending. This is the first tutorial I've presented, and the first tutorial we've presented for Gemmini in particular as well. So, if you have questions, let us know. If you have suggestions for future tutorials, maybe if you thought some of these interactive activities were kind of uninteresting, or maybe could be made more interesting, or maybe we're moving too fast or moving too slow, just let us know. We'd like to get better. And thank you for attending. I know we got people from all around the world, from like time zones where it's probably way too early or way too late for you right now. So thank you for taking the time. Hopefully you're not too sleepy tomorrow morning. Yeah, and that's all. So if you guys have more questions, we'll hang around. Or if you just want to chat, we can hang around, or we can chat about anything you'd like to chat about related to this research. Just let us know. And somebody asked about the slides and video. We are recording the video. We will share the video either on YouTube or Dropbox. We'll post it on the website. and we will also share the slides. And these new scripts that we've added, we will merge them back into master very soon. So hopefully they help, they make the tool more usable for people. Thanks. I'll just be sticking around.
Thanks for the tutorial. It's very informative. Yeah, so I have I think a very high level question about the compiler. So what is your, can you give a little bit details or elaborate about the compiler for Gemmini? Where is it from? Did you guys develop it? Or did you guys extend it Onyx compiler and add your ISA instructions?
So Gemmini isn't like using LLVM or something like that. The closest thing we really have to a compiler is the Onyx runtime, but that's more of a, what that's basically doing is just we provided like a set of implementations for different kernels, and it's just mapping those kernels as it comes across them to the accelerator. So the compiler story could probably be improved. We considered like, using Haylighter or something for this to program it, and we are now working with another team. We're going to submit this soon to PLDI, where we have tried to develop a Haylight-like programming language that can allow people to write their kernels for Gemmini much more easily, basically, than writing out the ISA themselves. So that might be another layer in our stack later, like using a Haylight-like language to program it and do some of the loop transformations more easily. But yeah, but I guess right now we don't really have a very sophisticated compiler. We're just using Onyx runtime for that, and it's calling handwritten implementations. Does that make sense?
Yes, so I think you basically on the Onyx runtime, you basically crafted the kernels and how that, so like you write handwriting kernels, how it's compiled to Onyx runtime. Is it compiled with I'm not sure if the Onyx runtime has their own specific compiler, or is it you just compile with LLVM? And yeah.
Yeah, I mean, yeah, we're not using LLVM. Let me maybe write a simple pseudocode here. So it's not that like sophisticated, honestly. It's more like a op in the Onyx graph. So Onyx just gives you a graph, right? It's just a file format. So we just loop through the different ops, and if the op is in Gemmini ops, then we'll map it to Gemmini. So run the op on Gemmini. So Onyx runtime is a self-file format, and there are libraries which will let you load that into your own data types. The Gemmini code itself, like these kernels, like this handwritten kernel, is it's written in C. So it's compiled by an ordinary GCC compiler, or you could use Clang or whatever you want. So it's compiled by an ordinary RISC-V compiler. Let me try to find the slide. But we have put in like macros, basically, like assembler macros that insert our custom instructions into that stream. So the compiler just inserts them into the binary, but it doesn't really know what those instructions do, right? So the programmer is responsible for knowing what those instructions are going to do. So maybe that limits right now the compiler's ability to optimize the code because it doesn't actually, though those instructions are kind of black boxes to it. Yeah, so right now the programmer is responsible for tiling those and maybe unrolling those and stuff. The compiler doesn't do that. But in the future, like I said, we're working on a new language to maybe make it a lot easier for the programmer to do that.
I see. So these macros are the ones that you mentioned, these primitive and the complex.
Yeah.
And the API is providing the header file, right?
Yeah.
Okay.
Yeah. So
okay. Yeah.
Yeah. I mean, we can also like look at it here. Sorry, if you want like a kind of solidify it. So these are macros, which other macros other people wrote. If you go up the chain to where this is defined, at the end, it's really just going to be like an ASM where they're like, I don't remember the exact syntax anymore. Like they're like actually constructing the binary like data, and that's just insert into the instruction stream. And then any normal RISC-V compiler can handle that.
I see. Yeah, makes sense. Okay, cool. I think the next question is again very high level. I just so I know, for example, TVM, the VTA, they have some ability to generate Verilog from the HLS, and I think I'm not sure where it is today. So I think these definitely looking at this Gemmini, it's definitely full stack. You guys have all these TLB, even the impact of TLB communication between the host and the accelerator. So overall, like, do you see like any difference between just the accelerator part? I think you guys have a weight stationary and output stationary, different kinds of data flows. So any like specific advantages, like other than the ones that I mentioned, like TLB, you have obviously when you say the full stack, you have these different memory, you can explore different memory hierarchies and communications, and what other specific advantages that you guys have over, for example, other frameworks like Magnet or like TVM or TVM BTA, I think, or NVDL. Like,
yeah, we actually had a table in the DAC paper where we compare ourselves to Magnet and whatnot. So it's at a high level, like across these different formats here or others in the paper, we basically identify specific features that they don't have. Like maybe they don't give insight into the virtual address translation system.
yes.
Maybe they only support one data flow. Maybe they only support one kind of spatial array. And we kind of try to show that we support a superset of what they support. For VTA in particular, like I am aware of like some technical differences. So they have a different way of handling loops. I believe they actually have like it was not 100% clear to me from their paper, but I think they actually have like loop instructions basically. I could be wrong. That was what I thought the paper said. Was trying to say, where like their loops are more flexible, whereas ours are more like hard-coded instructions where you instead give flags to decide how to like change the loops. So that's also kind of why we're trying to create this new language, so that people don't rely on those flags but can write their own loops much more easily, without if they can't rely on the complex instructions. So they can write those loops with the same performance with the primitive instructions. They don't have a reservation station. In fact, originally the way we implemented dependency checking was the same way that VTA implements it. We got the idea from their paper, but VTA has a stronger compiler story because of TVM. So it's easier for them to handle those dependencies basically. Whereas for us, it was we were we the person, we're the programmer, so that was much more difficult for us to do.
Okay.
Yeah. Yeah, I think you summarized the difference as well. Maybe they have they have perhaps a better programming language through the TVM, whereas we use C. At the same time, C is easier to integrate. It's easier to deal with in environments where you can't rely maybe on all of the libraries that TVM needs to be installed. Yeah, and other than that, they handle the gems a little bit differently. Other than that, the accelerator is doing. Right, and the other thing I forgot to mention, it's right here. They actually have instruction fetcher. So you have to put your TVM code in one particular region and then tell the accelerator to fetch it. Whereas our programming model is maybe closer to like the RISC-V vector specification, where it's interspersed. At least I believe it was interspersed. Yeah, does that make sense? Simon,
Yes.
Okay. Simon also posted a link to our paper. We have the table where we enumerate different things that we expose that they don't expose, or that they do that we don't do. But VTA is a great project overall.
Yeah.
It's like part of our inspiration.
Thank you so much. Yeah, I think I will just hang around in case other people have questions so that I give them a chance. Thank you.
Yeah, thank you.
Hi, I have a question. I have a question regarding the ROCC interface. So since Gemmini is using ROCC interface, does that mean for the current state, it could only be connected to Rocket and Boom? Because that's what the chipyard document says.
Yeah.
ROCC is only supported by Rocket and Boom.
Yeah, I was going to mention it, but I skipped over that by accident. Yeah, that's right. So you need a CPU which implements the ROC interface. So right now that's basically just Rocket and Boom. It doesn't, it could be any other CPU could implement this interface, but most of them, as far as I'm aware, have not yet implemented this interface. So yeah, like adding AXI support, I think we had somebody looking into that for a class project a while ago, but I don't think anything came out of that. Yeah, so that is actually another difference between Gemmini and some other accelerators. And VDLA is much more decoupled, right? Like through the AXI interface. Whereas Gemmini is very tightly coupled to the CPU. Not like completely coupled in that they still have different like caches, but coupled in that it's receiving instructions directly from it. So the ROC interface.
I see. So another question then will be, so is there any plan to kind of release the documentation for ROCC interface?
I think there is.
Is there because
I don't think there is a formal definition. Yeah, maybe I can. So that would be more, I think, the Rocket chip or the chipyard folks.
I understand more of a chip question.
Yeah, I can ask them though, like in person. I can relay to them that people apparently want this. There is yeah, the only, I think there were slides from a classroom somewhere. That was the closest thing I'd found to documentation. Maybe over here, if you search for ROC, you might be able to find them from an old class. But yeah, I can ask about whether they're planning to release like a full document. But
I see.
It's like, just to go over very quickly, very quickly. It's not that complicated. Your chipyard IntelliJ is kind of slowing down. You get commands which are just this full RISC-V command. You output a busy signal, and you have access to a PTW, and we communicate back to the accelerator just through writing to direct memory. But there is also like an RD like slot for instructions which return results. So yeah, it's not very complicated, but I agree that maybe that is something that's missing right now, a formal like specification. I can ask that.
Yeah. One other question is, so are we assuming all the, for example, in the future we want to connect a, I would say, custom core rather other than Rocket and Boom? Is it assumed that we have to write everything in Chisel?
No. So you can generate the RTL for the accelerator, like the Verilog for it. and you can find in that generated source directory. It is unfortunately kind of hard to read by sight.
Yeah.
But, it's all there, and then you could just import that into your own Verilog project. But you would have to, I guess, implement the ROC interface. You can also go the other way around. Chisel has support for like interoperability with like Verilog through something called like a Chisel black box. So you could also write Verilog components and put them on a SOC generated by
I see.
Shipyard. Yeah.
I see. Thank you.
Yeah, you're welcome. This is actually a question that I think comes up with Shipyard a lot. People, yeah. The Berkeley stack is very vertically integrated, so we try to make it flexible and interoperable with other stacks. But maybe that does scare people. Chen, were you raising your hand or?
Yes.
Okay.
Thank you for the sharing and great presentation. I would like to ask the question about quantization because based on your slides, I'm sorry, I forgot the page number. And after the data goes through the historical array, and then he will go through the value and then pouring. I didn't see you mention the quantization module here. So how do you quantize your?
So there's a script in Onyx runtime. It should be in the Onyx runtime README. Maybe I should have gone over that as well. I can do that for future tutorials. So there's a pre-processing script which takes like CNN models, for example, or like BERT, I think as well, or RNNs, and it tries to apply it tries to do a post-training quantization pass on it. So it leaves the classifier layer unquantized, but it tries to take the layers which typically perform well under quantization, and just find the averages and everything like how you would typically do quantization. For layers which are left unquantized, unfortunately, this means there has to be like a dequantization pass when you're going from one to the other. So if your full network can be quantized, then there's no like overhead to the quantization, right? You just run all the way through. But if certain components are like sensitive, like classifier layers can sometimes be sensitive. I've read that batch norm layers can sometimes be sensitive in training. So if you have layers which are sensitive, then there is a runtime cost, because then there has to be a conversion from the floating point values to the integer values in between. Right now, that's done on the CPU, but maybe there are also vector accelerators on Berkeley. So in Shipyard. So one thing we're thinking of is incorporating those vector accelerators as well, and they can handle some of the floating point stuff that an integer Gemmini doesn't handle, like those dequantization passes. Does that answer your question?
Thank you. I'm not fully understand, but thank you for that.
Thank you. Okay, we're past time. I'll still stay on until everybody else hangs off, and I'm free to keep talking if anybody wants to. But I won't hold anybody on after 1 p.m. So yeah, thanks again for attending, especially for people who are like, it's like 5 a.m. where you are right now. I appreciate that.
Thank you very much for the presentation.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you. It's a great tutorial. Thank you.
Thanks for coming.
Yeah.
Thank you.
Thank you so much. Yeah. Just I think I just messaged you. So curious if you are interested in a given talk at industry.
That could be possible. Could that go through my my advisors? So do you know Sophia Shao? I can write her email into here.
Okay. Then I'm gonna. Yeah, I think I know. Yep.
Okay. She usually handles like the industry talks for us.
Great.
Yeah, but Yeah, if you go through, that would be great.
Okay, great. I'll write an email and also CC you.
Yeah,
Thank
sounds
you
good.
so much.
Yeah, thank you.
Great. Yeah, very informative. Thank you so much. Bye.
Do you want to stop the recording?
Oh, yeah. Oh, maybe I should have done that before the final questions, actually.
Yeah, we can crop things.